Today's problem is course schedule 2. This kind of thing. It's a common problem. Course schedule 2. So I mean that implies that there must be a course schedule 1 problem as well. I've seen these on LeetCode as well. Course schedule 2. There may be course schedule 3, 4. I'm not sure, but it's they're directed graph problems. So difficulty is medium. You are given n courses labeled from 0 to n minus 1 in a 2D array prerequisite where prerequisite I equals x, y, which indicates that we need to take course y first if we want to take course x. Seems backwards to me, but that's the way they're doing it. So we don't have a directed edge in this case from x to y. We have a directed edge from y to x. It's really the reverse of the way that's usually represented, but okay. Find the ordering of courses we should take to complete all the courses. There may be multiple correct orders. You just need to return any one of them. If that is impossible, return an empty array. Actually, we're returning a list, so we'll return an empty list. Okay. Here's some examples. We'll work through one of the examples in the process of looking at the code. Constraints. N, number of courses, will be between 1 and 10 to the 4th. 1, 2, 3, 4, 10,000. Between 1 and 10,000 inclusive. Prerequisites size. The size of the prerequisites array will be between 0 and 10 to the 5th. 100,000 inclusive. Prerequisites, okay, so that just it's telling us that the prerequisites will be valid. They'll all be in the appropriate range. All the prerequisite pairs are unique, and a course will not have a prerequisite of itself. Okay, well, those are all edge cases, and we're given all of that. You know, if you're given this question and you're not given all of that, then you would want to ask, you know, am I guaranteed that the prerequisites will all be valid? Will they be unique? Will a course have a prerequisite of itself? And I mean, there's no reason for any of that to be true, but if it is, it complicates the problem, and then you would have to handle it accordingly. All right, expected complexities, O of n plus m. What is n plus m? N would be the courses. I guess m would be the number of prerequisites. Okay, that's reasonable. Topic tags. DFS, graph, BFS. I'm not sure how a depth first search would help us here. But, okay, let's take a look at this. First of all, I created a directed graph class. Okay, you don't have to do that, but I recommend that you do it. You know what we have in the directed graph class is an adjacency list, an in-degree array. I guess those are the important things. Now you could put an adjacency list just in the main method, and you could do the same with an in-degree array. But There's a reason why object-oriented programming is called object-oriented programming, and there's a reason why object-oriented programming is the dominant programming paradigm as I at this point in time. So if you're going to use graphs, directed graphs, it makes sense to display your ability to create and use objects. Okay, that said, what do we have here? We have a directed graph. We're going to create a new directed graph. The input to that is the number of vertices and the prerequisites. So what can we do from that? Well, that comes in, we'll store the number of vertices, we'll create an in-degree array. In-degree meaning for each vertex, how many edges are coming into that vertex? Or if you want to think of it in terms of this problem, how many prerequisites does a class have? Let's see. Okay, and then the adjacency list. We create a list, and we add to the list an initially empty list. The number of lists that we add is equal to the number of vertices, so that we can use each vertex. There's v vertices, they're numbered from 0 to v minus 1, and we can use that as an index into the array list to get the adjacency list, like how many vertices can we get to from this vertex? Let's see. Edges. So edges comes in, and for each edge we call the add edge method, and we do two things. We update the adjacency list. Again, it's backwards here. VW. But we update the adjacency list, and we update the in-degree array. All right, anything else? No, I don't think so. But actually, let's go ahead. Let me move this over a little bit more. Let's go ahead and get a pen and keep track of what we are doing here. Okay. So the adjacency array, whoa, actually before I do that, let me scroll this down so we can see it. All right, so we're going to use this example here. There are four classes and three prerequisites. So it's going to look like this. Why is that not moving? Oh, something. Okay. So the adjacency list then is going to look like this. The first one in is 0, 2. So 0 is a prerequisite of 2. Okay. Next, 2 and 1. So 1 is also a prerequisite of 2. And then 3, 2. So 2 is a prerequisite of 3. And then we have the in-degree array. Okay. The in-degree array will have, because there are four classes, four vertices, the in-degree array will have 4 elements like this. And as we create the directed graph, what we will discover is that 2 has an in degree of 2. 3 has an in degree of 1. 0 and 1 have no in degree. All right. So we've created the directed graph. We'll create a queue, and for the queue, we will check and see which vertices have an in degree of 0, meaning they have no prerequisites, and we can take those classes right away. So we'll put those in the queue, and those are 0 and 1. So, all right, let's put them in the queue. 0, 1. Array list order. This is our output. And maybe I should have done that a different way, but okay. And then the course count currently is 0. We have no courses in our ordering. All right, while the queue is not empty, and it's not empty, course equals queue poll. So we'll poll that. It's going to be 0, and we'll take it out of the queue. Order, add, course. So the order here, that is our course ordering. So yeah, okay, we'll add the course. So first course we're going to take is course 0, and course count will increment it. It is now 1. Looking for all the neighbors of course 0. It has 1, and that would be course 2. We can decrement the in degree of the neighbor, which is 2, meaning we have completed one of the prerequisites for that course. So there is a, well, let me do this first. 1. This decrement in degree, it's kind of a quirky method to have in a graph object, but we do need to be able to decrement the in degree. I'm thinking about this. What if, or we need something to remove an edge, and then that method decrements the in degree. But in any case, we do have a method in graph to decrement the in degree. Now, if the graph of that in degree is now 0, which it isn't, we could put it in the queue, meaning we've completed all the prerequisites for it, but we haven't. So we go back up. Actually, what, am I missing anything important down here? No, it's just when we're done, we'll look at that. Okay. Back up to the top here. While the queue is not empty. Poll the queue. All right, so if we poll the queue, we'll get 1. All right, get rid of that. Poll the queue, and it is now 1. So we'll add that to our course ordering. Course count is incremented. We now have 2 courses that we can take. Find the neighbors of course 1. The only neighbor of course 1 is 2. So we decrement the in degree of 2, and that's right here, and it becomes 0. If it's 0, then we can now put 2 in the queue, because we've completed all of the prerequisites. So, okay, let's go ahead and do that. Now, is the queue empty? No. Course. Poll the queue. All right. Now we get 2. Add that to the course ordering. Increment the course count. Does 2 have any adjacent neighbors? Yes, it does. 2 is a prerequisite for 3, so we can decrement the in degree of 3. Okay, so that now goes to 0, and if the in degree of 3 is 0, then we can put it in the queue. And actually, I should have polled this already. And into the queue goes a 3. Okay, queue empty? No. Int, course, queue, poll. Right? Poll the queue, and that gives us a 3. Order, add, course. All right, we'll add that. 3, 0, 1, 2, 3. Course count, increment. It is 4. Does 3 have any neighbors, adjacent? No, it doesn't. So, yeah, okay, so this doesn't apply. Yeah, this doesn't apply. There are no neighbors. Oh, we go back up here. The queue is empty. All right. Now, it looks like we've actually accomplished what we want to accomplish here, which is that we did find a valid ordering of the classes, and at this point we check and see if course count equals n. Course count is the number of courses that we were able to put in order. N is the total number of courses, and those are equal here. They're both 4, in which case we return this ordering 0, 1, 2, 3. Now, if that was not the case, then we would just create a new empty list and return that. Okay, so that's the algorithm. Let's get rid of all of this and then run it. I'm going to scroll all the way down here. All right, let's go ahead. All right, yeah, so if you learned anything from that, go ahead and like the video, subscribe to the channel, and we will see you next time.